This is the beam class, and we will study all the theory that we need to know to do especially diagrams of moments and also diagrams of shear. What is a beam? A beam is an element that transfers vertical loads horizontally. And the idea is that all the forces will be transferred directly to the base of the building. Normally, a beam involves bending and shear. We use the word checking a beam in engineering. And the idea is that we try to check, to test if the beam is working. And the points that we are testing are stability, that the beam will not fall over, adequate strength, I mean that will not break, and finally adequate functionality, that will not deflect too much. That is important because even if the building is stable and the structure is not breaking, when there is a lot of deflection, people will be afraid to use the structure. In order to do this, we need to know several things. First, the span and how it's supported, where the supports are located. That's what we call reaction 1 and reaction 2 in our case. There are also beams with 3 reactions that we will not be studying in this class. Later on, the load of the beam. Finally, the materials, the shapes, and the dimension of the beam. That will be especially important when we are doing a specific material. In this review, we will need to understand what is the type of moment and shear that are applying in the beam. Finally, a little bit upper, we will find also what is the strength and deflection that is allowed in each one of the beams. What we are trying to do, we want to determine the shape and the dimensions of the beams. And what we need to know, the span and how it's supported. The loads of the beams, the material, the strength. What are the loads that a beam is supporting? That is related with something called tributary areas. A tributary area is the area that a beam is supporting. For example, if we have a floor that we look here like a transparent color, and the floor system is supported by 4 different beams, those beams in yellow color will have a span, and that there are separate between them with a spacing. Well, the tributary area will be the area that the beam individually, each one of them is supporting, and usually is half the distance that separates the beam that we are calculating to the next beams. Well, a beam picks up the load halfway to the neighbors. Each member also carry their own weight. Well, all the loads that are located in this particular surface that we look here in gray colors are the loads that the second beam is supporting. And the area in gray color is half the distance that separates the beam that we're calculating, beam number 2, here with my mouse, and the next neighbor at the left and at the right. Well, the same happens with columns. Columns generally pick up a load from halfway to the neighbors and also carry the loads that come from the floors above, obviously. When we have a type of building like this, the corner of the building will be supported by the beam that is in the corner. And the beam in the center will support the area that is around. Something very important to understand is that if you have a beam that is located just in the corner, it will support only half the area to the next beam. If the distances are the same, usually the central beam will be supporting more weight than the corner beams. However, architects many times will make the corner beams bigger to emphasize that they are more important. Happens that sometimes, depending on the distribution, the one in the center will support more weight. Every element will support some loads, and one of them are the dead loads. That is very important to understand, and these questions are always in the test. How you calculate the dead load is a code value per cubic foot of square meter. This can be confusing because also you have a code value for the live load. But remember, the live load will be what we were looking before. You have a beam or you have a column is supporting an area, and you will have a specific number that you will multiply by the square footage of the area. In the dead load, no, is per cubic foot. That means you will multiply the volume of all the elements that the beam or column are supporting. They will have a weight, and the codes will give us what is the weight of all the elements that is supporting. You can have a column that is supporting several other columns, and is supporting a floor, and is supporting some machines, and the weight of those elements is the dead load, are the elements that are not moving. It's not related with the people, it's not related with furniture. For example, this column is supporting a wall, and this wall have a length, have a thickness, and have a height. Well, this load particularly is made with bricks. Well, we will take the weight of each one of these bricks, and we will finally understand what is the load. If not, we will look what is the height, the length, and the thickness of this particular wall. We will have a volume, and the material will have a specific weight per volume. For example, we can tell that this particular type of bricks will have for every cubic inch or feet, a particular weight of, for example, 20 pounds. Well, we'll multiply 20 pounds by the total volume of this particular element. The live loads are different. We'll have a carry that is an area that is carried by one beam or one column, and that area is in square foot. And we have a code value per square foot. And we will multiply by the area that support. For example, if we have a specific function, this particular column is supporting some machines, it's an industrial building, well, the area, the weight of this particular square feet will be very, very high in comparison with something that is like residential. Obviously, the live loads are loads that are not exact. We don't know exactly what machines will be there. We don't know how many people will be in a residential buildings, but the codes try to calculate a number that is quite high. And that number normally is multiplied later on by a specific factor to make it even higher. Well, the total load will be the area of the live load, the dead load per square meter or square feet, plus the cell weight of that material, because the material have a weight, that beam have a weight and need to be supported. The loads in beams are of several types, and we already looked some of them. We look point loads, concentrate loads. We can also have moments in the beams, what we are not calculating in this particular case. But for effects of this review of structures 1, when we have a beam, we can have a distributed load, or we can have a point load. Remember, when we have a distributed load, we have two denominations. We can tell the distributed load is, for example, 100 pounds or 100 pounds per feet. If the total weight is 100 pounds, we don't need to multiply by the length of the beam. But if it is not, we need to multiply. In order to get this easier in the test, I will also have a weight that is not general. I mean, we will have always weights like 10 pounds per feet, 20 pounds per feet, and you will always need to multiply by the extension, I mean the length of that distributed load. What the loads do? The loads and reactions will bend the beam, will try to also shear through it. This is bending. The force in red color will try to bend the beam, but also can cause a shear, can break the beam, as we can look in the inferior, in the drawing that is located below. What the loads do? When the load is applied, the material will bend. And as you know, usually in the superior part, we will have some compression, and the inferior part will have tension. I mean, in the area that is above, up in the beam, will have compression, and the area that is below will have tension. And there is always an axis, and this is the neutral axis, where we will not have tension, we will not have compression. The shear will tend to break the beam in this way. Something important to understand is that the beams are calculated according to the bending. That is the most important. If the bending is okay, then we check if the shear is okay. Unless the beam is very short or the load is punctual and is located in a very small, I mean, in a beam that is not long enough, shear will be more important. But usually, most of the time, bending is the most important element. Well, beams usually fail because of bending. Columns are different. Columns will break for different reasons, will fail for different reasons, and if the column have an area in section that is very small and the area and the column is very tall, usually that column will tend to have some kind of bending. And we already know that that bending has a specific name. What is the name of the bending that a beam has? Please review the slides before in past week to understand is if you forgot that. Well, we designed the beams, and in architectural structures, bending moment is more important. The importance increases as the span increases. Short span structures with heavy loads, then shear is dominant, as I explained. For example, in connecting engine parts. Beams in buildings are designed for bending and checked for shear. Well, how we quantify all those effects? Well, we need to know all the forces, the loads and the reactions. We need to make the beam like a free body. We will cut out everything that is supporting this beam, and we will imagine how this beam is working. We will find the reactions using the conditions of equilibrium. Well, what this means? We have a beam like this one, we will have a force in the superior part, and this force will have a value, imagine 100 pounds. Well, we know that the reactions will be 50 and 50 pounds because the beam is symmetrical. Well, let's look at cantilever beam, for example. You have a cantilever beam, you have a load. We use the free body idea. It's like we cut the beam. Now it's free in the space, and we need to look what is necessary to have to get equilibrium. Well, we have a vertical load that is called W in red color here that is acting in this yellow cantilever. When we cut, we imagine what happens in the corner. It's like the wall is not there anymore. What will happen? Well, this force W will need to have another force that is contrary in green color that is also called W. Now the system is in equilibrium. Vertical forces are equal to vertical forces. W is equal to reaction that is W. The deal is that this W also will produce a moment. I mean, it's not only that W will tend to bring this beam down, like going down, like sinking, is not only that, is that that element will produce some kind of bending like this. The beam will tend to bend, and that is a moment. And the moment will be that force multiplied by the distance. Well, in the extreme of this beam, we have two forces in order to get equilibrium. W multiplied by L, that is force multiplied by the distance, that is the moment there, and also a force W that need to push up. If not, that beam will like fall down, like go down. Well, we need all those forces to have some kind of equilibrium. If we cut the beam in a different place, for example, not in the stream, but in a section that we will call X, the same will need to happen. W will have another force that is called V, a reaction, with the same value, W. And the moment will be equal to W multiplied by the distance. In this case, the moment is called like minus W multiplied by the distance. But this is a convention. We will decide what is positive, what is negative. Well, if we have a beam like this, the shear diagram will be in this way. I mean, this force W is a force that is pushing the element down, and the force in the stream is pushing the element up. We go up, nothing happens, we go down. Shear will be constant, because in any place that we cut this beam, we will always have a contrary force that is W, the same value. If we cut here, we need to have the same value. However, the bending will be different. The bending will be inclined. Why? Because in this point, the bending or the moment will be almost zero, because it's W multiplied by a number that is very small. That number starts to grow, 1, 2. Let me go back. 1 unit, 2 units, 3 units, 4 units. If W is equal to 1, will be 1 by 1, 1. 1 multiplied by 2, 2. 1 multiplied by 3. 1 multiplied by a very big number, then we will have a very big bending moment. We will not study cantilever beams in the test, but it's important that you understand and remember what you studied before. Where we have here another cantilever beam, and we have some ideas how the shear and the moment are calculated. And this is with a distributed force. I will pass this because we don't have those kind of beams in this test. Let's plot the shear force diagram. You already know to do that from past time. When you have a beam, you will create a line, you will go up R1, nothing happens, you will straight. Another beam, you go down, nothing happens, and you go straight again. Another force, sorry, that is called W, you go down, the same weight that now is distance in the graph, and after nothing happens, and W have a weight, and well, that weight will be plot. You see, W is bigger than the other ones by coincidence, and finally we can close the diagram. These kind of diagrams, if you have problems to understand, they will be explained better later on. But the important here is to get the theory. When we have a shear diagram and the forces are punctual, like point forces, it's obvious that the shear will be like blocks. You see? We don't have curves, we don't have inclined lines, we have blocks. And that's the shear diagram. Well, point loads will produce a block diagram, and distributed loads will produce a triangular diagrams. Because the force will go up, and little by little, each one of these elements have a particular value that is pushing down, and little by little will be going down. If the total value here is, for example, 100 pounds for the full distributed load, we go up 50, that is half because it's symmetrical. We go down little by little, 100, we arrive at minus 50, and we go up 50. Well, I know that you already know this, but it's just a review. Well, when we speak about the shear, if we are speaking about timber, like wood, the kind of split can be something like horizontal. Shear is not important normally for steel, it's seldom important and critical. And the concrete needs special shear reinforcement. What happens with the concrete is that we'll have some pieces of steel that will be there, trying to put together the superior and the inferior pieces of steel in order to eliminate the possibility that they will separate. Well, there are sign conventions for bending moments. I don't want to go over this because, for example, our textbook have a different one, completely different. But some people tell that, well, sagging is a negative, hugging is a positive. And I don't think that that is something that we really need to worry about that. The important is that you understand when the moment is positive and when it's negative in relationship with the rest of the element. Well, thinking in a happy diagram, I don't feel that is particularly important, but I want to introduce that here because you will saw that in many books. Well, the important is that we try to do it in the same way that cantilevers can produce a negative moment and simple beams can produce positive moments, and so on. Well, we can tell, for example, that when we have a diagram like this, the important is that the green force that is in the left is going up. Well, we want to go up. Okay, this is the moment diagram. It's not a shear. If not, we'll have like a block. But because it's the moment, it will go up little by little, and after we'll go down little by little. And it's obvious this force that is in red color is going down. Well, from here to the right, the element go down. And this one is going up. Well, from here to the next one to the right is going up. I don't recommend to do this. Even if you do this in the test, I will consider if your number is negative, I will consider that as a possible good answer. But I recommend to do it in the same way that is in the book and the way that we are doing. Well, point loads will produce triangular diagrams. This is a beam, and the load will be like this. In the cantilever will be different. I mean, the moment will be zero near to the force, and after will grow. But as I explained you, we will not study cantilevers. In this review, we are studying only beams that are supported in the string, that are the normal usual beams. Well, here, look, we have a force going up. The shear diagram will be a block. We go up, nothing happens. We go down, nothing happens. We go down, nothing happens. We go up. But for the moment, it will be this type of diagram. And that will be explained later on easily if you don't understand. Well, distributed loads, for the contrary, will produce a parabolic diagram. I think that the video where it's explaining what type of diagrams we got, that is the last video of YouTube in this chapter 2, will help you to understand this a little bit better. Well, we have shapes of the beams, and the most important is that we have maximum values. Well, the maximum value is fundamental because if we know what is the maximum shear of the maximum moment, then we can calculate what type of beam we will need. We can go to Home Depot, get a table and tell, well, I want a piece of wood, let me look which one I need. This particular piece of wood have a maximum moment, a maximum shear that will resist, and then you can choose that one. Sometimes we need to draw the deflected shape that is exaggerated. For example, in this case, the deflection will be something like this. There is nothing in the middle to push in the middle of the beam to push the beam down. Well, those forces will tend to make this like a sagging figure. And that will be the diagram. In this case, for the contrary, it will tend to do like this. And that will be the diagram. or like that. If we have 3, that is not our case. Well, there are some formulas that we can use, and I imagine you study in structures 1 how to calculate the moment. For example, if we have a weight W in the middle of a beam, that weight have a specific value, imagine 100 pounds. Well, obviously the reactions will be 50 and 50 because it's in the middle, and there is a specific formula that is WL divided by 4 to calculate that moment. I don't need that you learn the formulas. You will be provided with the formulas. There are only some few formulas, I believe that 3 in the whole class that you may want to learn, and you need to learn. And we already spoke about that past class, and those are the formulas of stress, strain, etc. And this is the bending formula. This is just to remember, but you don't need to know these formulas by heart, and we will not have those kind of problems in the test. We'll have normal beams with loads in the superior part, and that's it. But if we have a bending, that will be the type of diagram. And this, if we have a distributed load, that will be the type of diagram that you will get in a beam that is in cantilever. And also we have some particular bending moment coefficients in some type of beam cables, and the figure how the bending will be. This is important to understand a little bit what happens. For example, if we have a beam with a load in the center, the maximum bending moment will be in the center. You see? If we have 2 particular weights separated by a distance that is symmetrical, again, the maximum moment will be in the center, in the place between those 2 weights. And we have 3, it will be in the center, just where is the last one. And in beams that are in cantilever, the same happens. Look, the moment is maximum in the streams here. Sorry, the shear is maximum in the case number 3 in the streams, and pass through 0 in the center of this W. Very important thing, because when the shear is 0, the moment is maximum. Again, look here. We have this particular case. We need to go up because we have a reaction. We go down little by little. We pass through 0 in the center. We continue going down because it's symmetrical. I mean, if W is 100, again, the reaction will be 50 and 50. I go up 50, go down little by little, inclined line 100, go up 50. The shear pass through 0. Then I calculate these particular areas. That's something that we will explain later on. And I will have a moment diagram where the moment maximum, the highest, will be in the center, the same place where the shear have a maximum, a minimum moment when the moment is 0. And there are formulas to calculate all this stuff. But those are the typical cases that are very easy. You have a beam that is separated the same distance, you have a beam that is in the center, you have a distributed load around all the beam, but sometimes that is not the case and we cannot calculate those formulas. Well, what we will do is that we need to do the diagrams, and that is what we'll be doing in the last class of this particular section. What the bending and moment does to the beam, it causes compression in one phase, tension in the other. It causes the beam to deflect. That is what is going on inside of the beam. Look, compression and tension. Those fibers become compressed, those become extend. Nothing happens in the center because we already explained that we have a neutral axis. How to calculate the bending stress? Well, it depends of the beam cross-section. It needs some particular properties of the section. Well, we need to know the beam to do an exact calculation, but for effects of these structures, one review, we will just imagine that we don't have this big and shape, but we have a section of the beam that is neutral and flat. Our beams for diagrams are completely flat, and we will do those kind of problems.